So, we have seen that what is the minimum fluidized velocity or the condition at which the particle starts moving corresponding to that velocity, which is the minimum fluidization velocity, and the height is the minimum fluidization velocity condition. Height and velocity is already said, and of course, before the fluidization starts, the packing was compact. Now, when the fluidization has started, packing will be little if it was close packed, now it will be a little loose packed, and that void corresponding to that is called minimum fluidization void under minimum fluidization condition, right. So, let us now find out what is the height, what is the velocity, all these let us now find out. Okay. So, let us see that what it is. It is that we can determine this length, right, and height of this. Now, we said that before onset of fluidization, if the porosity is epsilon, velocity is b prime, and the length is length or height, whatever we call, this corresponding to this we said, and here we had. So, particles were like this. So, this was the height or L, whatever we call, right. Normally, in most of the books it is said L, right. You can also use nomenclature as H, does not matter, as long as you define, right. Length or height, that L, and epsilon V prime, and pressure drop delta P, right. So, this is before onset of fluidization, right. Now, the area of the cross sectional area of this is CSA is equal to A, and which is uniform, right. Then we can say the volume of the bed that is equals to L into A into 1 minus epsilon, right. If epsilon is the void, the remaining solid is 1 minus epsilon. So, area is uniform. So, L is the height. So, volume is that L A into 1 minus epsilon, right. Now, this under minimum fluidized condition, under minimum fluidized condition, this under minimum fluidized condition, if we say corresponding to epsilon, it is epsilon mf, velocity is V mf prime, length is LMF, right. Area remains same, area of the particles. In that case, we can say that the volume of the bed under minimum fluidized condition this can be said equals to L mf into A into 1 minus epsilon mf, right. Now, if we assume that there is no porosity, so here we have that container and the particles are like that, it is highly compact, right, no porosity, right, epsilon is 0, then it becomes the full solid particles, right. In that case, we can say the volume of the particle then we can say that volume of the particle having no porosity that should be equals to L into A, right. A is the area, cross sectional area, and L is the bed height. So, that is the volume of the particles which is containing in that container, right. So, then we can say that this L into A volume of the particle that must be equals to L mf times A times 1 minus epsilon mf, because same particle is there. This is the height under fluidized condition, particle sectional area remains same, right. Epsilon mf got changed, earlier here it was 0, here now it is new epsilon mf, right. So, the particle remaining is 1 minus epsilon mf into A into L mf, that is equals to L A, right. Therefore, we can write L mf that must be equals to L times A over A times 1 minus epsilon mf, right. So, this we can say is nothing but L over 1 minus epsilon mf, right. So, we can easily then write that L O1 A 1 minus epsilon 1 must be equals to L 2 A 1 minus epsilon 2 etc., dot, right. That means, we can say that L 1 over L 2 is equals to 1 minus epsilon 2 by 1 minus epsilon 1. Same is true here, that is L mf over L is equals to 1 over 1 minus epsilon mf, right. Here it was no epsilon, no void. So, there is y by 1 by this, right. So, this we can say what is the minimum height when we have got minimum fluidization, or we have got fluidization, that time corresponding to the bed height is the minimum fluidized bed height, right, or height of the bed under minimum fluidization condition, height of the bed under minimum fluidization condition, that is LMF. So, LMF we can find out if we know the L, that is original height of the particles when there is no void, right, and in that condition we have seen that the relation between the void as under fluidized condition and the initial length or height of the bed, that is related as LMF over LMF over L is equals to 1 over 1 minus epsilon MF, right, where epsilon MF is the void under minimum fluidized condition, right. So, what we can then write is that L MF is L over 1 minus epsilon MF, say we note it to be 1. Next comes, this is the length of the bed under minimum fluidized condition. So, we can write length of the bed under minimum fluidized condition. Right, LMF. So, next comes what is the pressure under fluidized condition. So, pressure drop under minimum fluidized condition. What is that? Right? Now, in that case, we have to do the force obtained from the pressure drop times sectional area must be equal to the gravitational force, as we have said, extended by the mass of the particles, that minus the buoyancy force, right, of the displaced fluid. So, if we say that if we do the force balance, by doing force balance, we can write that the pressure drop times sectional area this is the cross sectional area. Okay, let us also write cross sectional area, right. This must be equals to the gravitational force minus this gravitational force exerted by the mass of the particles by the mass of the particles right, by the mass of the particles, and we can also say this minus the buoyancy force. Buoyancy force of the displaced fluid, right. So, this if we write mathematically, we can write delta P A, that is equals to L M F A into 1 minus epsilon M F times, right, rho, right, times P minus rho, right, into G, where rho P is equals to density of the particle and rho is equals to density of the gas or fluid. Right. So, we got that delta P A is equals to LMF A to 1 minus epsilon MF into rho P minus rho into G. This is equals to, we can write that delta P over LMF, this is equals to 1 minus epsilon MF, right, by, or one more 1 minus epsilon MF into rho P minus rho, right, this into G. Delta P by LMF is AA goes out, uniform cross sectional area. So, delta P by LMF is equals to 1 minus epsilon MF into rho P minus rho into G, right. So, this we can say to be equation 2, right. Now, we can write Ergun's equation as delta P by L, that is equals to 150 mu V prime over phi s square d p square, right, into 1 minus epsilon whole square over epsilon cube plus 1.75 rho V prime square over phi s dp into 1 minus epsilon over epsilon cube, right. This is the Ergun's equation. Right. So, if this is the Ergun's equation, so at minimum fluidization condition, we can say at minimum fluidization condition, we can say that this Ergun's equation we can rewrite as delta P MF also at minimum fluidized condition over LMF. This is equals to 150 mu V prime MF divided by phi s square into dp square, because particle size will not change, because we said uniform sectional area, into 1 minus epsilon MF whole square by epsilon MF cube, right. So, this we can rearrange as 1 minus epsilon MF times rho P minus rho, right, into G. So, this must be equals to 150 rho V average, VMF prime over phi s square into dp square, right, whole into 1 minus epsilon MF square over epsilon MF cube, just rewriting that, right. This plus 1.75 rho VMF prime over phi s dp right, phi s dp into 1 minus epsilon over epsilon mf cube, right. So, 1.75 into rho V m f prime by phi s dp into 1 minus epsilon m f by epsilon m f cube, right. So, this is the Egan's equation as required by you. In this case, we have said that so 1 minus epsilon m f rho p minus rho into g, this is that Egan's equation. Okay, fine. So, if this is true, then we can also write or rho p minus rho, right, into g, this is equals to 150 mu b m f prime over phi s square dp square, right, into 1 minus epsilon m f over epsilon m f cube, right, plus plus 1.75 into rho VMF prime square by phi s dp into 1 by epsilon cube times dp cube rho by phi s dp cube rho by not phi mu square, right. So, this is what was dp cube rho by mu square dp cube rho by not epsilon mf. Okay. This is true, but dp cube rho, right, rho p minus rho into g is equals to 150 rho v prime mf phi s square dp square 1 minus epsilon mf by epsilon mf cube plus 1.75 rho v m f prime square by phi s dp, right, multiplied by 1 by epsilon mf cube, right, multiplied by 1 by epsilon cube, right. So, this is no more required. So, now we can rewrite or dp cube multiplying all along mu square rho p minus rho into g, this is equals to 150 mu VMF prime divided by phi s square dp square right, phi s square dp square into 1 minus epsilon mf 150 mu Vm prime phi square dp square, right, 1 minus epsilon mf by epsilon mf cube. We multiplied both the sides with this dp cube rho by mu square plus 1.75 rho Vmf prime square right divided by phi s dp minus this plus 1 by epsilon mf cube into dp rho by mu square, right, dp rho by mu square, right. If this is the Ergun's rearranged condition, we can further rewrite that dp cube rho by mu square into rho p minus rho into g, this is equals to 150 by phi s square or phi s cube into 1 minus epsilon mf whole square by epsilon mf cube into phi s dp Vmf prime into rho, this divided by phi s cube is where epsilon mf cube there. So, mu 1 minus epsilon mf, right. This plus 1.75 over phi s cube into 1 minus epsilon mf square over epsilon mf cube right into phi s dp v prime f mf, right. So, phi s dp v prime mf into rho divided by mu into 1 minus epsilon mf, right. So, this on rearrangement we can write 1.75 by phi s square into 1 minus epsilon mf square over epsilon mf cube n r square plus 150 by mu 150 by phi s square, sorry, phi s cube into 1 minus epsilon mf square divided by epsilon this 150 by phi s cube 1 minus epsilon mf by epsilon mf cube in R E, right. This minus dp cube rho by mu square into rho p minus rho into g. This is equals to 0, right. So, we have found out that a relation using Ergun's equation, right, with NRE. This is a quadratic equation, NRE square, NRE and a constant. So, b square minus 4ac plus minus 4ac plus c square, right. So, this we can b square minus 4ab plus b square a square. This we can use plus minus b that finding out root, that solution and get the correct value. Okay? Thank you.